questions? All right, so we were then working this last problem here in 8.4. We made some manipulations in our trig substitution, and this is where we're at. All we need to do is fill out secant in terms of x at this point. Just kind of clean it up a little bit too. So 12 natural log of absolute value of secant. So that's going to be the square root of our x plus 1 squared plus 36 over 6 secant theta, and then we have minus theta. I forgot our substitution. So our theta was going to be based off of our substitution here. So theta is going to be the inverse tangent of x plus 1 over 6. Plus c. Okay. So that's basically it. That was, that was a sort of a, I don't know. It was nice to see it worked out that way. I don't know that I would have worked it out that way, but we certainly were able to figure it out. I think it would have. Well, let's finish this up and then talk about it. So we've got 2 natural log. Our quantity here is positive, so we'll just have the natural log of this quantity. Minus inverse tangent. 1/6, sorry, 1/6 here as well. Okay, and so we could apply the trick here. I forgot this. We could apply the trick to this if we wanted to rewrite this in terms of or utilize properties of logarithms. We could probably clean that up a little bit, but that's kind of it. All right, any questions on that example, the way we chose to work it? So I think, like when we said right here, let's let tangent be this x plus 1. When you think about tangent squared plus something for the substitution, if we were just to take this thing, instead of trying to substitute a trig function here immediately, we could have made a u substitution. We won't work this out fully, but we'll make a u substitution here. So we have our u squared plus 36. Our du is dx. And The 2x plus 1, we could account for that because the u is just x plus 1. So we can account for the 2x plus 1 in terms of u, because basically we have x in terms of u. So we just, manipulate this a little bit and say u minus 1 is equal to x. But we needed 2x plus 1. So we have 2u minus 2 is 2x. And then add 1, 2u minus 1 is 2x plus 1. And so if we look at it this way, now we don't have x plus 1 over 6 to substitute for a trig function. We could just kind of look at it as u tangent of theta equals u over 6. And I don't know that that's less confusing, but we could also break this integral up into two separate ones and have two u over u squared plus 36 minus 1 over u squared plus 36. So do we know the antiderivative of 1 over u squared plus 36? Hopefully you do. So there's inverse tangent of u over 6. What about this one? 2u over u squared plus 36. Yeah, that's just in logarithmic form, right? The derivative of the bottom is already on top. So that's ln absolute value, u squared plus 36, and this is minus inverse tangent, minus 1/6 inverse tangent of u squared over 6. So we could take that approach and not ever have to do a trig substitution. So just keep that in mind when you're doing these. It's sort of, like I said, the more techniques you have, the more difficult it can be sometimes, because you've got all this stuff going through your head. Which one should I use? What will work? But this will work without a trig substitution. Okay. So any questions on that example? That is it for set 8-4. All right, then we'll finish off at 8-4 then with that example. 8-5 is our last integration technique. The rest of the unit 8-9 deals with improper integrals, and then chapter 9 we look at 9-1 and 9-3, which are introduction to differential equations. So it's like a really basic introduction. But the notion of partial fraction decomposition is basically, it's like taking apart a rational function into its smallest components. So a couple of examples here, like both of these are rational functions, but when we can simplify something like this, we should. So this thing here on the left, we can simplify that. And really no other tactics are necessary. So it's 4 plus x to the negative 1 minus 5x to the negative 2. So once we simplify, that's a very straightforward integral. But something like 2x minus 1 over x squared minus 5x plus 6, not as easy to integrate. You can't simplify the integrand, but what we could do is break that rational function into its individual pieces. So it's kind of based on the idea of taking the rational function and factoring it. And then determining or basing the breakdown off of what kind of factors do you have in the denominator. Okay, so I think there's a cleaner example here. Like if we have to integrate a rational function like 3x over x squared plus 2x minus 8, that's sort of a difficult thing to integrate. But through the methods of partial fractions, we're able to rewrite that function like this. And then now that's something that's, we can integrate pretty easily. Okay. So that's, in a nutshell, the method of partial fractions. You break your fraction up into smaller fractions, and then those should be more manageable than what you started with. So this integral is equal to this integral because the integrands are the same. And then a lot of times with these linear factors on the bottom, like x minus 2x plus 4, you're just in a situation where they're in logarithmic form, or use substitution if you have to. But this is just the natural log of the absolute value of x minus 2 plus 2 times the natural log absolute value of x plus 4. So that's really the idea in this section. The methods that we utilize to do that, are sort of algebraic in nature. But before partial fractions, you make sure the rational function's in lowest terms, the degree of the numerator. The degree of the numerator has to be smaller than the degree of the denominator. Otherwise, it's improper, like we saw in 8.1, and you have to use long division. So the steps are just the factor of the denominator. Depending on what the factors are in the denominator, dictate sort of your setup after that. So there's 4 types of denominators that we'll encounter. Simple linear factors. We'll just put a couple of examples here, like x minus 1, 2x plus 3, stuff like that. Linear factors. And then repeated linear factors are just any of those raised to a power, like x cubed, x minus 1 squared, 2x plus 3 to the 5th, stuff like that. Simple irreducible quadratic factors. So these are irreducible. Things like x squared plus 1, etc. The idea of an irreducible quadratic comes from the fact that if you could factor it, or if you did factor it, the quadratic would have imaginary factors. So do y'all remember the discriminant in the quadratic formula? The thing under the square root. The quadratic formula was quadratic formula square root of b squared minus 4ac. So like that part of the quadratic formula, if that b squared minus 4ac was negative, then you had negative solutions to your quadratic. So you had imaginary solutions to your quadratic. So if you're ever unsure if it's an irreducible quadratic, all you gotta do is check, is b squared minus 4ac smaller than 0? And if it is, you're not gonna be able to factor the quadratic. You can factor it in terms of like imaginary numbers, but it's not factorable over the real numbers. And then 4th is the repeated irreducible quadratic, so like x squared plus 1 to the 5th, and so forth. So depending on the function on the bottom and how it factors in one of 4 ways, or you could have a combination of those, but each one of these items, 1 through 4, have a different sort of setup when we break it down into its partial fractions. Okay, so the procedure for partial fractions with the simple linear factors, we're going to rewrite that as a over x minus 1, a2 over x plus 5, etc., etc. Most of the time we don't have that many factors to worry about, so we could just use a, b, c, and d. Instead of a1, a2, a3. So like a specific example. If we had like x over x plus 1 times x minus 2, we would set that up. We've got simple linear factors in the denominator, so we're going to have a over one of those factors, x plus 1, plus b over x minus 2. So that's really the first setup. You got to recognize what factors are in the denominator. That dictates how you're going to set up the a, b, c, d, etc. And then, of course, we've got to solve for a and b here. That'll give us the full partial fraction decomposition. Partial fractions for repeated linear factors. We've got a constant over our linear factor, another constant over that linear factor to the second power, and so forth until we exhaust that power. But still, it's just a constant over the linear. It's either one of these. If you've got a linear factor, it's just a constant over the linear. So, like for example, if we have 2x plus 3 over, I don't know, let's say x plus 2 cubed. We've got a repeated linear, so we would say that's equivalent to a over x plus 2 to the first plus b over x plus 2 squared plus c over x plus 2 cubed. So for something like that, we would have to solve for a, b, and c. Usually we don't see more than like 3 or 4 of these things, because I mean, if we had, if you had like A1 all the way through A12, and you've got 12 unknowns you have to solve for. So you have to have like 12 equations to solve for 12 unknowns, and so it can get pretty tedious to do things outside of like 3 and 4 terms. Partial fractions with simple irreducible quadratic factors. These are now not a constant, but now a linear over the quadratic. And we would have to find out what a and b are in this case. So you don't see a lot of these by themselves, but like if we had 4x plus 3 over x squared minus 4x plus 5, let's do that b squared. Yeah, that would be okay. So something like this, is that irreducible? Let's make sure it's irreducible first. 16 minus 20, yeah. Okay, so something like that. We really can't do much with it, but according to the breakdown, if it's a simple irreducible, or if it's a irreducible quadratic, we have to set it up as ax plus b, and we figure out over the thing. So in this case, like for this example, it doesn't really do much for us, but we have a specific example at least. We don't see any repeated irreducible quadratics, but if we did, it's kind of the same pattern. Like if this were, let's just say like this were squared, we would have ax plus b over that thing to the first, and we would have a cx plus d over that thing squared. So it's the same pattern sort of as the repeated linears would take, but we don't encounter those, so I'm not going to write any of that down. Yeah, those are the procedures for the particular factors in the denominator. So again, good candidates for partial fractions would be rational functions. So other methods that we've seen that could potentially work is we could try to complete the square on the bottom and then split up the integral into two pieces. Certainly doable in many instances. But if you can do partial fractions, usually that's easier than completing the square, splitting up, u substitution, you know. So we're gonna take, bring it off to the side, we're gonna take our 3x plus 5. And we're gonna factor the x squared minus 4x minus 5. And say, all right, well, it's 3x plus 5 over x minus 5 times x plus 1. We've got our repeated, we have a rather simple linear factors. So that's going to tell us that we need to equate this to a over x minus 5 plus b over x plus 1. So that's just something like that procedure. You've got to know how to set that up, because from here we're going to need to solve for a and b. And the way that we do that is we just multiply through by the denominator x minus 5 times x plus 1. So that clears the denominator over here. We get a times the quantity x plus 1 plus b times the quantity of x minus 5. Does that make sense? We're just multiplying both sides. Multiply both sides by x plus 5 times x minus 1. Sorry, x minus 5, x plus 1. My bad. The x minus 5s cancel out over a times x plus 1. The x plus 1s over b cancel out b times x minus 5. Okay. And then, yeah. So there's kind of two approaches we could take. There's a shortcut to solve for a and b that doesn't always work. And then there's the sort of the longer route where we have to solve a systems of equations. But we'll go ahead and look at both of them, because the shortcut does work here, but it doesn't always work. So we'll say the long way, I guess. The long way is to, you've got to equate like terms to solve for the coefficients. So we're going to take the right-hand side and multiply all of that out. So we have ax plus a plus bx minus 5b. And then what we know is that if we, sorry, I said bx, I didn't write it, bx minus 5b. What we know is if I add ax and bx together, that has to be 3x. So I'm going to take my x terms, my ax and my bx, and those have to be 3x. So that gives me one equation. 3x has to equal ax plus bx. In other words, we can just ignore those x's now that we have this established. In other words, a plus b has to be equal to 3. And And we do the same thing for the constants. We got a positive A and a negative 5B. Those have to equal 5. So just put that here. 5 has to equal A minus 5B. So that's the system we need to solve for A and B. Sometimes, not anything that we do, but it is entirely possible that these systems are so large that you have to put them into a matrix and reduce the matrix to solve. Sometimes that's the most efficient way. I don't think we don't see any of those, but they're out there. So solving systems, you've got a couple options. Elimination, you could substitute. It's totally up to you how you want to do that. But if we just subtract these two equations from each other, the A's will go away and we can solve for B. So if I take equation 1 and subtract off equation 2, I have 3 minus 5, A minus A, and B minus 5B. Does that make sense? It might have been a while since we've solved systems of equations, but we can totally subtract these two things. So if 6B is negative 2, which means B is negative 1/3. So where does that B go? Well, it goes up for this B that we said was the decomposition of this fraction right here, right? So this B, just keep it here. We know that's negative 1/3. Now that we have B, we can easily find A. So we're going to plug this back into, I don't know, equation 1. Equation 1 says 3 is equal to A plus B. Solve for A. So 3 plus 1/3, 10/3. That means A is 10/3. So the longer way to solve these is always to just equate the powers of x and the constants, and then solve that system of equations. Is 10/3, we'll write that up here as well, so we can remember what that is. Well, I don't. Yeah, I think we'll have enough room there. But does anyone have any questions on any of that? Okay. The short way, I guess, would be so we'll just stipulate that it does not always work. Sometimes it may work in part to help you get like A or B or C, but often when it doesn't work, it's not going to get all of those variables for you, or those whatever parameters. Okay, we have to take this right here. Just write this out here, please. So from here, instead of like multiplying everything out, What we could do is, based on the factors next to A and B, there's two things we can do. One, we can let x equal to -1, because if we let x be -1, then that's going to eliminate the A portion for us. Okay. So if x is -1, we have 3 times -1 plus 5. 3 times -1 plus 5. A times 0 is 0, and then we have b times, maybe we could have put that over here, b times -1 minus 5. Again, what that tells us is we've got 2 equaling -6b, or b is -1/3. I'm sorry, my arrows are really bad. They're arrows. So if we had a bunch of repeated factors, like if we had a times x plus 1, b times x plus 1 squared, c times x plus 1 to the third, if we plug in x equals -1, then we just zero out the whole thing. It doesn't help us. Okay, then we're going to let x equal to 5 to zero out the b stuff. So second step would be going to let x equal 5. Plug that in for all of our x's. We have 15 plus 5 is 20. 6a and 0b. So 6a equals 20. A equals 10/3. So no system to solve, just kind of plug and go. Most of the times I would say you could utilize this technique to at least get you one, A, B, C, or D, and then from there your system becomes a lot easier to solve. Any questions on this? So either way, you come up with B is -1/3, A is 10/3, so we need to put those back here. And then instead of integrating the left-hand side, we're going to integrate the right-hand side. So we have the antiderivative of 10/3 over x minus 5. B was -1/3 over x plus 1. Now, the choice of factors is arbitrary. Somebody might have said that, well, it factors as x plus 1 times x minus 5. That's fine. You set it up like we did, solve for A and B. No matter how you set this up, the number above x plus 1 should be -1/3, regardless of where you have it, and the number above x minus 5 should be 10/3. Okay, so what is the antiderivative of 10/3 divided by x minus 5?
10/3 is natural log, absolute value x minus 5.
10/3 natural log absolute value of x minus 5. Do y'all agree with that? Okay, similar thing, -1/3 natural log absolute value x plus 1. So there's our answer. Any questions on that? All right. of behind, I think. Yeah, so we might skip this example because we're behind. But this is very akin to our first example. We factor the denominator, you've got linear factors on the bottom. Set all that up. You can totally try this if you want. I'm just gonna write down the answer. So we can catch up, hopefully. So you can kind of, I don't know, maybe you can kind of see the way it unfolds. The x plus 1 times x minus 2 is our denominator. That's over a, which is 3. This is over b, which is 5. So you can work that one if you have time, if you want to. Look at a few with repeated linear factors. So you've got x squared over x plus 1 cubed. So repeated linear factors, we just have to count for all powers of the linear factor. So we're going to have a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. So again, we've got to solve for a, b, and c. Okay, so we're multiplying all of this through by the denominator here on the left. So we have x squared is equal to what? A times
X plus 1 squared.
x plus 1 squared. Yeah. Plus b times, we have the cubed over the square. Do the first. And then we have our cubed over the cubed. So we've got to solve for a, b, and c. So here, notice if we let x equal -1, the a and the b are gone, but that allows us to pretty quickly solve for c. So even though the shortcut won't fully work here, it at least gets us a part of that, which I think if you can do that, then why not? It's much easier. So we're gonna do that. We're gonna let x equal -1. We have -1 squared. A and b are times 0. So we have c is equal to 1. And so we'll sort of keep that in mind that we have this. But the rest of it, unfortunately, we've got to take the long approach now. So we've got to multiply all this stuff out and then equate powers of x. So we have our x squared, we have our ax squared plus 2ax plus A plus bx plus b. See, I'll just go. Well, I'll just leave the c as it is for now. We could, in theory, plug in 1 for that c because we know it's 1. Equating our x squared, we have an ax squared. That's it, right? Ax squared. Sorry, x squared equals ax squared, which means. So that means also a is equal to 1. We have our 2ax and our bx equaling what? 0. Yeah, there's no x's over here. So we have 0 is 2ax plus bx, which means that 2a plus b is equal to 0. So we already have c and we already have a. All we need is b, and we can solve b from this equation by itself. Because we have a. But we're going to go ahead and finish. We have our constants a and c also equaling 0. So we'll write that here. A plus b plus c has to equal 0. We don't really need both of these equations to solve for b, but the general rule of thumb is as many unknowns as you have to have that many equations to solve for them. So we can use either one of these. We already know b, and we already know a, and we already know c. We can find b from either one of those equations there. A was 1, b, and c was 1 as well. Yeah, c was 1 as well. So we got b equaling -2. We have 1 over x plus 1 minus 2 over x plus 1 squared plus 1 over x plus 1 cubed. Anyone have any questions? All right, now we integrate that expression. First one's logarithmic form. How about the second and the third one? What are we going to do there?
The second one is a bit like 2 over x plus 1.
Is this one 2 over
X plus 1.
x plus 1? Yeah. So we can think about here, we've got a u to the -2. Here is u to the -3. If you have to do a u substitution here, it's not a big deal, but dx. So it's a pretty straightforward u to the negative 2 du integral times negative 2. This one here, I'll use w, not v, because we already do integration by parts with d's and dv's, or u's and v's. So just to not accidentally multiply those together. Okay, so again, u is that. This is integral of u to the negative 3 du. Everybody okay with that? Okay. Just powers of x. You don't really have to, when you have like x plus a number to a power, you don't have to worry about its derivative being divided, because its derivative is already 1. Let me scoot this down. Okay, so we can just kind of finish this and write it all to the right. So the antiderivative here, u to the negative 1 times negative 1, or divided by negative 1, times the negative 2 here. To u to the negative 1, same thing with this one. U to the negative 2 over negative 2. And the first one was logarithmic form already. So we've got, well, I guess, I don't know, we'll leave the negative exponents. It's 2x plus 1 to the negative 1. Minus 1/2 x plus 1 to the negative 2. Let's see. So yeah, if you're checking this, then you've got a bunch of stuff to add together, right? Because the integrand was just one fraction. So take the derivative, you get the common denominator, and it's kind of like you're working backwards from this step right here to get to this thing right here. Any questions on that? Okay. So irreducible quadratics, like 2x plus 1 over x squared plus 121. If we're just going to set up the partial fraction decomposition, again, we would just look at it as 2x plus 1 over this denominator. Irreducible quadratic, we have to write this as ax plus b over the x squared plus 121. So that's the setup. You can see from the setup, though, it's not going to help, right? If we solve for a, we're going to get that it's 2, and if we solve for b, we're going to get that it has to be 1, right? But that's how we would set up if that were our denominator. How else would we or could we try to evaluate an antiderivative of that function? Trig substitution, yeah. So we've got a square plus a square on bottom. So partial fractions doesn't actually work on this, because you just get the same thing in return. We could do a trig sub on this. So the next few are just to set the partial fractions up. We're not actually going to integrate them. So here in example 5, we've got a combination. We've got a linear and a irreducible quadratic. So for the linear, we're just gonna put a over our linear, so a over x plus 3. And for the irreducible quadratic, we have a bx plus c. And so it's kind of an aside, but we do see it. How would we, once we have this thing here, how do we integrate this? Like if that was, if we solve for b and c, let's pretend we know what b and c are.
Split the function.
So when you're in this position here, generally when you split it up, it'll be very manageable. So like this would be the integral of bx. If you split it up like that, this one here, of course, inverse tangent. This one here is virtually in logarithmic form, or it's a Hughes substitution. So that's how we'll handle those when we come across. How about the x plus 1, x squared plus 4 cubed times x plus 2 squared? What kind of factor is x? Linear, right? It's x minus 0. So we have a over x. We have another linear, x plus 1, so we have b over x plus 1. X squared plus 4 cubed, that's a irreducible quadratic, repeated. So we need to have a linear over that, so we're going to use cx plus d. I guess we'll use capital. Cx plus d over x squared plus 4 to the first. Ex plus f over x squared plus 4 squared plus gx plus h over x squared plus 4 cubed. And then our last one, linear repeated. So with our linears, we just need a single constant. So maybe we say I over x plus 2 plus j over x plus 2 squared. So something like that is a bit, difficult to work with. But most of these factors are different. You can let x be 0, x be negative 1. Here you can let x equal negative 2. You can solve for quite a bit of those for a few values of x. But we won't see anything like this lengthy. They're just way too time consuming. In theory, we could do them, but nobody would want to do them anyways. That's the setup for that one. Any questions? Yeah.
So how about if we have like x cubed plus 4?
Like that?
Yes.
And it's just over something?
Yeah.
Well, we don't really see those either. It's just, it's either or, linears or quadratics. I know this, well, could that be?
Yeah, I think unless it's a quadratic or a linear, it's possible to factor it down
Yeah.
to a combination of those two.
You can factor cubes, but I don't know about this one.
The cube function has to cross the x-axis at some point, so it has to have a root. So
Has that as a real root, yeah.
you'd have to be able to factor it.
Yeah, so you could maybe only have one real factor here, but we don't see cubes. But they could be broken down linear times quadratic. Same thing with fourth powers, quadratic times quadratic, linear times linear times linear times linear, stuff like that. Yeah, any other questions? So this problem we'll work on. I think we'll take a break first. It's sort of, well, it's not that lengthy, but I don't think we get it done in 10 minutes. So we'll take a break, look at this example. There's one more also that we're going to look at in 8.5, and then we'll move on to 8.9.
Word formation, cost me $250 to, and he did it under the table. Well, he did it under the table, so. But if it's snowing outside and your blower motor's not working, you literally have no heat because there's no air. So your windshield won't.
All right, this one was on the previous page. We set it up, but we didn't integrate it. So we'll go ahead and do this problem here. 18 over. All right, so we're going to say that that's equal to our linear x plus 3, a over x plus 3, and our irreducible quadratic. Multiply through the denominator, we get 18 is equal to a times x squared plus 9 plus bx plus c times x plus 3. So there's not anything we can use to zero out the a. We can zero out the bx and the c with x equals -3. That way we can at least know what a is. So let's do that first. We've got 18 over here still. 3 squared, 9. 18a is equal to 18. So from here we can determine that a is 1. But we're going to have to multiply everything out to find b and c. Okay, so a is 1. We've got 18 equals to ax squared plus 9a. Plus bx squared plus 3bx plus cx plus 3c. So we get three equations total. Our x squared terms, a and b. No x squared over here, so a plus b has to equal 0. So if we know a plus b is equal to 0 just from that equation, we know also a is 1, so we know what b is. So we've got our a is 1, b is -1, we need to find c. So the easiest, I think, I don't know, I guess there's two other equations we get from this. Are x with 3bx plus cx, that's also 0. And then that tells us that 3b plus c is 0. And we know b is -1. So 3 times b plus c is 0. -3 plus c is 0. So c has to equal 3. So we have our a, b, and c. That's all we really need from that, so there's no need to say that 9a plus 3c is equal to 18. You can write that out. It's not going to give us any additional information. So with our a, b, and c, we're going to go back up to our breakdown here. 1, -1, and 3. So we have our fraction is equal to 1 over x plus 3 plus b is -1 plus c is 3, and that's all over x squared plus 9. Any questions on this? Now we're going to integrate that expression on the right. Where'd the thing go? All right. Guess it just disappeared. All right.
You wrote it down at top left of the.
I thought we had like a whole like typed out.
Well, yeah, but I was just curious if you didn't remember it. It was written.
A whole typed out thing. Oh well, we'll just rewrite it. So we now know that to be the antiderivative of 1 over x plus 3. We got plus a negative x plus 3 over x squared plus 9. As we mentioned on the previous page, this negative x plus 3 over x squared plus 9, we're going to split that up into two different integrals. We have integral of 1 over x plus 3 minus the integral of x over x squared plus 9 plus 3 times the integral 1 over x squared plus 9. So notice the first one, logarithmic form. The second one, it's almost in logarithmic form. Derivative of the bottom is 2x though. So So if we put a 2 here and multiply this by a half, it's in log form. And then the third one is an inverse tangent. So you have natural log absolute value of x plus 3 minus 1/2. Natural log absolute value of x squared plus 9, which we don't need absolute value around that. That's always positive. But just in general, get in the habit of using absolute value. Plus 3 times, what's the antiderivative of 1 over x squared plus 9? Inverse tangent of x over 3. What do y'all think?
1/3 up front.
Yeah, the 1/3, 1 over 8, inverse tangent of x over 8. 1/3. So we have just the inverse tangent of x over 3. Is that what you were thinking about, the overall result? Yeah. Okay, good. Plus some constant. Any questions? All right. So we've got one more to look at, but you know, in all honesty, we've got what, integration by parts. I guess the trig integrals, I wouldn't really count because they were all identity based or use substitution based. Trig substitution and partial fractions. So we've got basically like 3 new techniques. So as you could imagine, there's many integrals that we still don't really take care of with those 3 methods. So if you're going on, you know, there's countless other techniques that you could employ. Usually these are the most common ones though, for sure. So evaluate this 2x cubed plus x squared minus 6x plus 7 over x squared plus x minus 6. So,
In the first thing, we should make divide top to bottom.
right, good. So the first thing we should notice is that the degree of the numerator is larger than the degree of the denominator. So this is an improper expression. It's an improper integrand. We need to use long division. So we're gonna use long division first, and then see what we're dealing with after that. So we need a 2x here. So we can have a 2x cubed plus 2x squared minus 12x. And then just remember to subtract off all of those terms. So 2x cubed minus 2x cubed. We've got an x squared rather, minus a 2x squared. We've got a negative 6x plus 12x. And then we're going to bring down the 7. Start over, we need a negative 1. So we have negative x squared minus x plus 6. We're subtracting all of that off. I guess I'll put this here. 0, we've got a 6x plus x. You've got a 7 minus 6. So that's what we should end up with. Our quotient should just be x to the first, because 2x cubed divided by x squared is 2x. That's some stuff. And so here's our stuff. So after long division, then this integral becomes what? Or the rational function becomes what?
2x minus 1 plus 7x plus 1 over x squared plus x minus 6.
Right. You have to take your quotient plus your remainder over your divisor, x squared plus x minus 6. That's a
7x
dx.
plus 1, right?
Yeah, 7x plus 1. Thank you. All right. So 2x plus 1, or 2x minus 1 rather, we can handle that. The 7x plus 1 over x squared plus x minus 6, how are we going to do that? We can try to complete the square, split it up, use substitution. We could try that route. How does or can we factor x squared plus x minus 6? Yeah. So what kind of factors do we have? Linear factors? Yeah. So since we can factor it like that, why don't we just do partial fractions? Completing the square, we have to take half of 1, add a fourth in, add a fourth, or subtract a fourth from the negative 6. So it doesn't look so hot when we complete the square. I mean, we could still approach it that way, but so that second integral is going to be evaluated using partial fractions. So I'm just going to go down here for space. This is I'll just rewrite what we have for right now. Partial fraction decomposition. Okay, so simple linear factors again. A over x plus 3, or whatever order you put this in. B over x minus 2. Solve for A and B. I'll just go for this there. Okay, so we've got to solve 7x plus 1 equals a times x minus 2 plus b times x plus 3 for a and b. So the shortcut method would solve a and b for us. We've got different factors. I'm going to let x be 2. And we have 15 on this side is 0 plus 5b. So B is 3. And we're going to let x equal negative 3. Get negative 20 equals to negative 5a. So I just put it down here. So a is 4. So it's really 4 over x plus 3 plus 3 over x minus 2. So both of those are logarithms. Antiderivatives are the logarithms for those. Write it down one more time. So it's 2x minus 1 plus 4 over x plus 3 plus 3 over x minus 2. Does that make sense? Does anyone have any questions?
I actually have a question.
Sure.
Yeah. Does it ever matter what's on the top? If it's like an x, like that's okay, but it's x squared, and then it kind of complicates things because if it's like x cubed over x squared, you'd have to do your own division.
Yeah.
But if it's just like an x, are we pretty safe
Yeah.
as far as that goes?
Yeah, it depends on what's on the bottom, but yeah.
Alright.
Yeah, you wouldn't see, I don't know that you would ever, like, you could have like x over x plus 2.
Oh,
you know,
okay.
something like that, but that's, you know, you probably wouldn't do partial fractions for that.
Yeah, that makes sense. Yeah, I'll have to look at it.
Yeah, yeah, most of them do like work out like we've seen.
Okay.
Yeah. So we have antiderivative of 2x, antiderivative of 1, antiderivative of 4 over x plus 3. And the antiderivative of 3 over x minus 2. And that's our answer. Are there any questions on 8.5? Okay, so we'll end 8.5 and start 8.9. So improper integrals are, there's two types. Either when you integrate towards, like out towards infinity, around like a horizontal asymptote, or when you integrate next to a vertical asymptote, essentially. So the interval of integration is infinite. For instance, the integral from 1 to infinity of the function 1 over x dx. It's like finding this area here. Integration, interval of integration is infinite, or we could have an integral that's unbound on the interval of integration. So like the integral from 0 to 1 of the function 1 over x dx. I don't know, not to scale, but we'll just say that's 1. So that area there. So yeah, you can integrate like up to a vertical asymptote. You can integrate out towards infinity, but both of those require concepts from Calc 1, which were infinite limits and limits at infinity. So if you're rusty on those, you probably should refresh. L'Hopital's rule shows up frequently with some of these as well, so that's something else you may want to look at. L'Hopital's rule also shows up when we deal with sequences in series, so it's good to know L'Hopital's rule. Limits at infinity come up all the time when we're talking about infinite series, so limits at infinity also don't really go away. So for these limits at infinity, B and C, E, F, D, H, and I. A couple of things to remember though, it really depends on the function. Specifically with rational functions like C, B, D, and I, limits at infinity only, we only need to look at the leading term of the numerator and the leading term of the denominator. So for like the limit of x plus 2 over x plus 3, we look at the leading term over the leading term. Because the lesser terms don't matter out towards infinity. They're not contributing very much. So out towards infinity, this function's basically x over x, which is 1. So that limit at infinity is 1. The limit at infinity for C is basically like x squared over x when we're really far out, and x squared over x is x, right? X is approaching infinity, this approaches infinity. So like the weird thing, what we'll see with these integrals like this, is even though if we integrate out towards infinity or up to a vertical asymptote, a lot of these things do still have a finite area, which is counterintuitive if we're integrating something that never actually reaches the y-axis. You know, intuitively we would think that there's infinite area there because it never actually touches the y-axis. The area never actually like gets cropped off at some point. But that's not the case. Some of these things have a finite area, some of them have infinite area. And so it's kind of counterintuitive. How about D? What's the limit at infinity for D? 0. Top is 2, the bottom gets larger and larger, quotient gets smaller and smaller. How about H? Negative infinity, right? Again, leading term here. You get -3 times an infinity cubed, basically. So a large number cubed is a large number times -3 is a large negative number, I guess. How about I? 3 over 4. Again, leading term over leading term. This function at infinity behaves like 3x cubed over 4x cubed, which is 3 over 4. Other things that maybe you didn't talk about, but sort of intuitively you know, are things like E and F. So like with leading terms over leading terms, it applies to things other than polynomials, but it gets kind of, you know, the terminology is not actually correct, and it can get a bit weird sometimes. But the idea is, if you've got like 4 over e to the x, and x is approaching infinity, we're kind of thinking of that the same way. The numerator is 4, the denominator is getting larger and larger, So that quotient has to get smaller and smaller. Conversely, f, the numerator's getting larger and larger and the denominator's staying fixed. So that has to go off to infinity. So like these kinds of things you should be able to evaluate rather quickly. You know, sometimes with L'Hopital's rule it does take a little bit of work, but you know, things like what we're looking at here, you should be able to evaluate very, very quickly. The other ones here, like A and G, I think that's it. Yeah, A and G, those are the ones that show up when we're integrating near a vertical asymptote, for instance. So like the ones here that we've done would be applicable in a situation like this one here, in number 1. And A and G would apply to a situation like this. So part A, as x approaches 3 from the right, what does x plus 2 over x minus 3 approach? Infinity? What do y'all think? Infinity? It's going to be infinity or negative infinity, right? Because your denominator is approaching 0. Your numerator is fixed at 5. So you've got 5 over a smaller and smaller number. That's a larger and larger number. How about 2 over x minus 4 as we approach 4 from the left? Negative? Do y'all agree? So we're approaching values 4 from the left, slightly less than 4, numbers slightly less than 4, minus 4, and negative. So again, the denominator is approaching 0, but it's approaching 0 through negative values. 2 over a really small negative number is a really large negative number. Okay, so those are the types of limits that show up with our integrals. Does anyone have any questions on that? If you need a refresher, these limits are in our textbook, section 2.4 and 2.5. L'Hopital's rule, again, L'Hopital's rule is in section 4.7. If you also need a review of that. But the basic summary is here. L'Hopital's rule applies to limits of the form 0 over 0 or infinity over infinity. Those two are the only two instances where we apply L'Hopital's rule. As you might remember, there's like 3 variations of L'Hopital's rule as well that you should be familiar with. You got an infinite product, 0 times infinity applies to L'Hopital's rule, just not directly. There was infinity minus infinity, and there was those funky ones like 0 to the 0, infinity to the 0, 1 to the infinity. And those 3 things are also L'Hopital's rule in disguise. So all of those should be addressed as well. There's potential for, any of that to show up. So a couple of these here, limit as theta approaches pi over 2, of cosine squared over sine minus 1. So really the first thing in evaluating limits is to determine what's the form I'm dealing with. If it's something like 2 over 0 or 5 over infinity, those things you don't even need L'Hopital's rule for. It's only 0 over 0 or infinity over infinity. Okay. So just ensure that you're determining what this limit is. We've got 0 over 1 minus 1. And then that way we know for sure that's indeterminate. If it were like 5 over 0, that's fine, it's going off to infinity or negative infinity. If it's 0 over 5, it's 0, right? So to make sure you know what form your limit's taking, and then when we apply L'Hopital's rule, it's usually asked that you put an H over the equal sign just to indicate that you're using L'Hopital's rule. We take the derivative of the top function, divide that by the derivative of the bottom function. Derivative of our bottom is derivative of sine minus 1 cosine, and derivative of cosine squared is 2 cosine theta times negative sine theta. That's the chain rule on top. Okay. And the other key aspect of L'Hopital's rule is it applies to 0 over 0 or infinity over infinity. But every time you apply L'Hopital's rule, you should simplify your expression first before you try to reevaluate the limit. Okay, so we're just going to simplify this as theta approaches pi over 2 minus 2 sine theta. Does that make sense? Might have been a while since you've seen L'Hopital's. So you have for sure seen it at some point though. So go back and review if you're a little rusty here. Yeah, because there's really no other easy way around it. Again, it shows up with sequences in series too. All right, so we've got -2 as that limit. So a limit like this, in example 3, e to the x over x squared at infinity, if you're familiar with growth rates, which we sort of rank functions in terms of their growth rates in the next unit, but growth rates are also like a really efficient way to compute limits at infinity. So something like this would evaluate to infinity over infinity, and we would say, all right, well now let's use L'Hopital's rule to take care of that. But growth rates say that comparing these two functions, an exponential and a polynomial, the exponential function grows much more rapidly than the polynomial function. So that limit should be infinity, just based on the function on top is growing faster than the function on the bottom. So if you're familiar with growth rates, you can say that this limit is infinity by growth rates. And maybe after this example, we can just write it out, just so we're all on the same page as to what we mean by growth rates, but they are applied for limits at infinity. Anyways, infinity over infinity, we're going to apply L'Hopital's rule again. Take the derivative of the top, divided by the derivative of the bottom. Derivative of the top, derivative of the bottom, L'Hopital's rule, simplify, you can't simplify, reapply the limit, it's still infinity over infinity. So we're going to apply L'Hopital's rule again. Now we have the limit at infinity of e to the x over 2, which is infinity over 2, which is infinity. We can just write that out. Any questions on any of that? So growth rates. We're not going to classify functions because they go all the way from logarithms, powers of x, powers of logarithms. There's exponential functions, there's factorials, there's those goofy functions like x to the x power, like all of those are sort of ranked in terms of the slowest growing to the fastest growing. But we don't see a whole lot of those, primarily like exponentials and polynomial stuff is what we see here. But the idea is that there's kind of two situations. One, and both of them are limits at infinity. So if you have a limit at infinity of a quotient, let's say f over g, and the way we're going to write it is either we're going to say that this limit f over g at infinity is 0. And if that's true, then which one of these functions, f or g, is growing faster? G, right? Does everyone agree that g has to be growing much more rapidly? So that's like just in the instance where you have like your limit evaluated like 5 over infinity. Just think about f of x. It doesn't like evaluate to 5 or anything, but it's like super slowly growing. But g of x is growing very rapidly. So you kind of have something comparable to that. So if this limit at infinity is 0, and g of x grows more rapidly, than f of x. And the other side of that, I guess, is what we saw with e to the x over x squared. If that limit is infinity, that means f of x is growing more rapidly. Than g of x. So this would be like x squared over e to the x, just to stick with that example, but it can apply to much more for that one. Sort of the reverse of that for this one. So like in the instance of that limit on the first page where it was 3x cubed, I think, over 4x cubed, it comes out to be 3/4. In situations like that, we would say that they grow at comparable rates. But these two cases are specifically geared towards functions growing more rapidly than other functions. So it applies to like, some of these limits on the first page as well, like this one here. We've got an x squared over an x. Like the x squared is growing much more rapidly than the x does. That's infinity. Part B, they're growing at comparable rates. So we can still look at limits at infinity through that lens a lot of times. And what it allows us to do is just kind of bypass L'Hopital's rule a lot of the times. So anyhow, does anyone have any questions?
And if they approach a finite number, they grow at the same rate?
Comparable rates.
Okay.
Yeah. Yeah, if they approach a finite number, it's a comparable rate. All right, so that's kind of the tools necessary for evaluating these things. Does anyone have any other questions? Yeah.
Rate of change has a lot to do with growth rate, right? Like, even though they're kind of different, like your rate of change is higher, your growth rate is higher, right? I don't know.
Not necessarily.
Think about it in terms of L'Hopital's rule. If you keep taking the derivative,
It's the
eventually,
rate of change.
if it's a lower rate of change, eventually the derivative goes away, whereas the other one still remains. So if you take
Right.
the derivative of e to the x a bunch of times, you still have e to the x. Whereas if you take the derivative of a polynomial, eventually that goes to a constant, right? Or 0. So yeah, the steeper the function, basically, higher growth rate it has, although once you get to like factorial and whatnot, you can't really take the derivative of that. So you have to think about it a different way. But
So growth rates and the instantaneous rate of change are different.
Yeah, they are different, yeah, you're right.
Because I mean, you could have like you say like a growth rate is just like which one's growing faster, but rates of change could be positive or negative.
Yeah, it's like a
So,
similar but different.
yeah, but yeah, I like your explanation. Okay, so when evaluating improper integrals, if the limit does not equal a real number, finite number, then we're going to call the integral divergent. If it does equal a real number, a finite number, we're going to call it convergent. And this terminology will follow us into the next unit when we talk about sequences and series, and it's super important. Convergence is what allows us to rewrite a function as an infinite polynomial. Okay, so we're going to go back to those first two examples we wrote down. Integral from 1 to infinity of 1 over x dx. So the idea is you've got to find sort of the improper part of the integral. In this case, it's infinity, and we're going to label it. You know, and how we're going to label it in class is just based off of the integral from a to b. F of x dx, a lot of times you can use whatever letter you want, but if the lower limit is goofy, I'm going to call that a. If the upper limit is weird, I'm going to call that b. You can call it t or s or whatever you want to call it. But the first thing is to identify what the improper portion of that is, and then relabel it as a letter. So we're going to call this the same thing as the integral from 1. Since it's the upper limit, like I said, I'm just going to call it b. You can call it t or w or whatever, of 1 over x dx. But we have to allow b to go to infinity. So that's kind of how we're going to handle these things. We're going to find the antiderivative, evaluate it from 1 to b, and then apply that limit to our antiderivative. So it's the last thing you apply is that limit. We're going to do that first, fully, and then apply the limit. Does that make sense? Okay, so we have this limit. What's the antiderivative of 1 over x? Natural log of the absolute value of x. And we're evaluating that from 1 to b. Over here. So we're going to plug in our bounds. And I see it. I've just, like in the past, people get really sloppy with this. So I know it's a pain to write this limit. If you want to find the antiderivative evaluated from 1 to b first, when you're done, then put a limit in front of it, I'm okay with that. But at some point, please put a limit in there and don't just like fill out stuff. Okay, I don't know that that's unreasonable at all, but it's really technical. Okay, so we have the natural log of the absolute value of b minus the natural log of the absolute value of 1. So that's just the 0, ln b minus 0. B is going off to positive infinity, so that b is a positive number. We don't need absolute value there. What's the natural log as b approaches infinity? Sorry, natural log of b as b approaches infinity? Infinity? Yeah, infinity. So what we say here is, we know that it's infinite. This integral from 1 to infinity is divergent. Meaning there is not a finite area from 1 to infinity. It's an infinite area. So hopefully you just remember that limit, because the natural log function is a very, very slowly growing function. So, I mean, it looks pretty reasonable until we start zooming out. Let's shrink this a little bit. But when we start zooming out of the natural log, it's very, very flat. So like the natural log of 200,700 is 12.2, right? But it still tapers off, goes off towards infinity, because we know what its inverse is. We know the domain of the natural log because we know the range of the inverse. Okay. So this thing we kind of just sketched here, that's an infinite area. So there's a lot of paradoxes with these kinds of things too. Your textbook does mention some of them. One of them is if we take that function from 1 to infinity, and we find the volume of this revolved about the x-axis, and we find the surface area of this thing, you know, it goes off forever, right? But what we find is that it has a what was it? It's a paradox in the sense that the surface area is infinite, but no, the volume is infinite and the surface area is finite, or something like that. So there's a lot of like those kinds of things. It's like, hey, you've got a thing that you can fill up, but you can't paint it. You got a thing that you can paint, but you can't fill up. There's figures that have infinite perimeter but finite area. So you like run into all these kinds of paradoxes. But it's based on this idea.
Would it even be possible to make one that's infinite in surface area but finite in volume? Because volume expands cubically, where surface area surface area expands squared.
Right.
So it seems like it would have to go off faster, but
Yeah.
counterintuitive either way.
Yeah, it might be. I don't know. I've never fully investigated that. I mean, some things that seem like reasonable are not. So I can't answer that
Especially with
100%.
infinity, so.
Yeah, right. Especially at infinity, and then that's the problem, right? Anything at infinity. Oops. Anything at infinity, then you start to have these issues, or paradoxes, where it's like it's both. They're both true. Anyhow, the other one we looked at when and I guess scenario number 2, integral from 0 to 1 of 1 over x dx. So what's the improper part here? What's the issue here? Yeah, so the 0 here, right? Remember, just as a basic thing, what this says is we're taking this function 1 over x. We're taking the function 1 over x, and we want to find the area from 0 to 1. But the problem is our vertical asymptote is here, right? So 1 over x, the domain of that function is all real numbers but 0, and we're integrating about 0. So that's the improper part. So we're going to rewrite the integral as the 0's the issue, so that's our lower bound. I'm just going to call that a. The integral from a to 1 of 1 over x dx, and we're computing the limit as x approaches, or sorry, as a approaches 0.
From the right.
Yeah, so you gotta have a direction on this too, right? Again, the graph can help. We're looking at this graph from 0 to 1. So if I'm talking about this area, I can only approach 0 from the right-hand side. So 0 from the right. So be super careful when you're doing that. We saw part A and G on the first page. Depending on the function and depending on what direction you approach it from, it's going to affect the sign. So 0 from the right. Again, the limit's the last thing we're going to compute. Limit as A approaches 0 from the right. We already know that this is going to end up as the natural log of absolute value of A minus the natural log absolute value of 1. As A approaches 0 from the right, what is the natural log approach?
I think it's the way just
The other way around.
Oh, yeah, sorry. Thank you. Certainly. So natural log of A, as A approaches 0 from the right, approaches negative infinity.
We're subtracting it since it's positive.
Yeah. Natural log approaching 0 from the right, negative infinity. You have 0 plus infinity, infinity. Again, diverges, infinite area. And so like if we did the same thing with the function 1 over x squared, we would see that it's convergent. You have a finite area. And so like when we compare the graphs of like 1 over x to 1 over x squared, you know, what's playing out is how fast the function flattens out. Like x squared flattens out much sooner than 1 over x. So anyhow, both of these are divergent. When we look at sequences in series, testing, like doing an integral on a series is one of the main tests we use to determine whether something converges or diverges. And you know, we kind of see that it's connected to what we're doing right now. So this kind of thing does show back up in the next unit as well. Does anyone have any questions on either of those? All right. So we'll leave that for next time. You can try it if you want, but what we're going to see is that thing actually converges. It's 1 over x squared instead of 1 over x. Y'all have a good weekend.